Good afternoon, everybody. Hope you're all keeping well. I've been enjoying the beautiful weather. Thank you for attending North Wales branch technical presentation, which is very kindly given by David Jameson from GWP Consultants. Sit back and always just a quick reminder, make sure you all the microphones are muted. So thank you, David. Over to you.
Good afternoon, everybody. Thanks for the opportunity to have a chat with you all. I thought when I got asked to do this, I would put together a short presentation, really, to demonstrate some of the interesting projects we've had over the last few years, or last year, in fact, which are to do with rockfall modeling in some interesting locations. I thought I'd give you a little bit on the background of how we go about modeling, both in two dimensions and in 3 dimensions, and then demonstrate some examples in interesting settings. So if you just bear with me a second. Here we go. So the outline of the talk follows the following. I'm going to talk about the reasons for rockfall modeling in the first place, a little bit on the evolution of rockfall evaluation, and how we go about doing some generic containment design, and discuss also where we might want to move away from that generic design and go on to something which does some more accurate modeling, so we can normally pull in the rock traps at the bottom of the faces. Consider the parameters used in analysis. Consider some of the engineering judgment we have to apply to it, because the rockfall modeling programs use algorithms which in some instances might not give you realistic bouncing and trajectory results. And then show some interesting examples over the last couple of years that myself and my colleagues have been involved with. Not all the examples I'm going to show I've modeled myself. My other colleagues at GWP have done those, and they've shared those with me for you to have some interesting examples of what's going on. So I'm going to look at a 2D modeling example in a Malaysian quarry, 2D and 3D exampling at Bardon Hill, where there's an interesting rope conveyor installation recently, and also a large slope failure on a hillside up in Scotland, and what we had to do in order to quantify the risk to those people who are going to work in and around disassembling the temporary power lines. And then just at the end, if we've got enough time, just to have a quick look at quarrying and the mend dips. So why do we want to actually look at rockfall in and around the quarrying environment? Well, for the statistics that I have available, where it breaks down rockfall incidents into structural failures or isolated rockfall events, you see that of the total number of incidents which were recorded in British quarries between 1969 and 1989, there were about 5% of all of those incidents resulting in accidents were from falls of ground. And from the rock faces, you can see that 2/3 were from rockfall incidents, which essentially are small blocks of rock detaching from the face. And we're talking about blocks of less than 10 tons, often less than 1 ton. And you can see on the box on the right hand side that the small failures often lead to the greatest number of fatalities and serious accidents on quarries. And that's why we try and keep people away from the faces as far as possible by the installation of either rock traps at the bottom of faces, or where you'll have to go close to the face, you might want to put some other containment systems in place. So let's just have a quick look at the evolution of evaluation systems for generic containment design. So if you just think about the mechanics of rockfall, it usually initiates either from a climatic or a biological event that changes the forces acting on the rock face. So climatic effects might include wedging out of blocks, small blocks on the face from repeated freezing or thaw cycles, or heavy rainfall events which cause increases in pore pressures behind the blocks, and weathering and degradation of the slope itself. Biological events, biological events might include movements which result from incidents such as tree growth or animal activity, or wedging out of the slope from, of rocks from the slope where wind is blowing against a tree and it wedges out a block from the face. But all of those are fairly low energy activities, and when you're in a much higher energy activity, such as construction, excavating faces and or blasting faces, which results in the blocks on the face being fragmented in any case, and then excavating those faces, leaving loose rock on the faces, you have a potential for mechanical initiation, which are several orders of magnitude greater than either of the other climatic or biologic events that I've talked about above. So we need to consider how we're going to constrain or contain any rockfall from faces. So in the past, physical restraints on the slope might be a series of constraints which are there to control movement on the slope. The little sketch on the right hand side is from the middle 70s and summarizes quite nicely the different techniques you might want to put in place for minimizing movement or controlling movement on the slope. So when you've excavated a face, you might want to control movement by installing, for example, drape netting, and that has the effect of reducing the amount of movement of blocks, but it doesn't constrain it. Blocks are allowed to fall behind the netting and into a rock trap at the bottom. If you're trying to actually constrain the block movement and reinforce the slope, you might have to install a number of dowels into the netting. But ultimately, materials that are falling down from the netting will fall into a trap, usually at the bottom of the face. And that can be an excavated ditch, or it might be behind a constructed fence. And in the quarrying situation, we often use rock traps. So generic approaches in the past have been worked on since the 1960s or so. And you can see on the right hand or in the middle, there's a generic approach to sizing the rock trap at the bottom of a slope. So this is looking at a slope which hasn't got anything to constrain the rock fall. And basically you have a look at the height of the face, consider the slope of the face, and generally what you see is steeper slopes, blocks from a face will fall directly into the trap at the bottom. Where they're slightly flatter, then it'll bounce out, and flatter again, gentler slopes, the blocks will roll down the slopes, and you can size your generic rock trap at the bottom of faces based on some height to slope ratios. Now that has been taken forward in the quarrying situation, where there's generic industry guidance for rockfall, which looks at individual face heights, and this is generally adequate on the whole when you've got fairly regular slopes. So we can see generic based rock trap designs which are industry wide, generally on a rock trap on a bench, you would size it such that the trap is 1/4 of the face height high, and the depth of that trap would be about 1/8 of the overall adjacent face height high. And you can see on the right hand side a typical trap on an individual bench being constructed there. However, there are other instances where you might want to get away from that, and we'll just have a look at now the evolution of rockfall trajectory modeling and rock trap design. Basically, what influences rockfall trajectories as blocks fall down from the face? In the photograph, you can see a slot cut through a face going down from one bench to a lower level, and a load of rockfall debris across the floor of that ramp. The geological conditions, the face condition is pretty much constant. You can see on the right hand side the overall slope, just generally the same. The condition of the face and the amount of loose blocks on that face is generally the same. The only thing that's changing is the height of the adjacent face. And you can see pretty much following the line of the shadow on the rock floor that the further you go down the ramp, the wider the rockfall footprint becomes. And that's a direct response to the height of the face and the amount of energy the blocks have as they fall down the face. So basically what we're saying, going back to that generic design, is that the height of the face and the amount of energy of the blocks dictates the width of the rock trap at the bottom of the face. So the primary influences on trajectory, excuse me, is to do with rock slope shape. And you can see for faces steeper than about 70 degrees, blocks falling on that face will generally fall straight downwards, won't catch on any ledges or projections on the slope, and will fall quite close to the toe of the slope. The faces which are a little flatter, generally between about 70 and 45 degrees, you have the bouncing action, so blocks falling from the face can catch ledges as they come down and maintain some develop some horizontal velocities which kick them out from the bottom from the face and can cause it to bounce quite wide away from the toe. And that little sketch on the right hand side there that shows bouncing, that might be an individual bench, face with projectile with promontories on it, or it might be several benches which are choked with debris, and so that could be a multiple bench situation there. For faces which are less than about 45 degrees, you mostly get a rolling type rockfall generated, and the amount of kick out from the slope itself often depends on rock shape. So your tabular type blocks, which can end up rolling end on end, can go much further than simple round, generally equi-sized blocks. So slope geometry is the primary controlling factor on rockfall trajectory. So how do you actually determine slope geometry? In the past, we were forced to, well, when I say in the past, I'm talking about the 1990s, there were some early rockfall models, and it was the overall slope was generally determined from crest and toe positions of from surveys, and the engineer had to go out onto site and look at each individual face and see and make an estimate of how much variability in slope there might have been on it, and then that variability can be input into a model to show the amplitude and wavelengths of any variation in the simple joining of two dots, the crest to the toe. From about 2000, but in doing that, sorry, just going back that, yes, you had to make some engineering judgments. And then later on, 10 years later or so, remote scanning techniques became fairly commonplace on quarries, and you were able to undertake some scanning of the face down the section lines where you thought perhaps rockfall might develop. However, you were often left with shadows based on where, or relative to where you set up your scanning equipment, such that quite often you wouldn't be able to see beyond the crest of benches, and so you'd have a shadow at the bottom of your slope. And again, the engineer would have to make some assumptions about what the wavelength and trajectory and frequency, asperity height might be at the bottom of that slope. But more recently, routine modeling, routine flights of quarries are now done by UAV drones, and you can get extremely comprehensive point cloud models from those surveys. And on the right hand side, that might look like a photograph, but actually it's a it's a screenshot from a 3D model, which has picked up all the variability in the shape of the slope. And if you angle your camera on your UAV drone properly, you can get a very accurate definition of the general slope that we're trying to model. Not only does it pick up the slope, but in this particular case, it's picked up the road conveyor line as well. So again, I just want to emphasize that slope geometry is the primary influence on rockfall trajectory assessments. So not only can we use UAV surveys to generate the slope orientations, we can also drape the photograph over the top of the triangulation that's generated from those surveys, and then collect structural data from those models as well. I show an example here of the rock slot developing at Bardon Hill last year, and all the structural data we can collect from that, which can give you information on not only the block sizes and areas of initiation of rockfall, but the orientation of the joints and spacing of joint and fractures, such that you can determine the size of blocks that might come out of the face. And if you think they're going to be unstable, then you can also size bolts and netting to hold all of that back. So other parameters we often use in the rockfall models themselves, other than the slope geometry, are coefficients of restitution. And these parameters effectively measure the retarding capacity of the surface materials making up the slope. So as your blocks fall from height, they impact on the slope. And as they impact on that slope, they essentially lose energy. And it's ascribing the parameters that tell the model how much energy is lost, both as a normal coefficient to the slope and a tangential coefficient to that slope, dictate the amount of energy then is available for it to bounce off the slope, and or bounce or roll or move further down the slope. So where you've got clean hard rock, you might have higher parameters of restitution, meaning that the blocks will eventually not lose as much energy and they'll bounce further than materials which are of higher energy absorbance, such as original ground, which might be peat covered, or you may have laid some gravel or energy absorbent material in the bottom of your rock trap to try and absorb the energy as it comes down the slope. One of the things that you have to be aware of when you do some modeling is that scaling of those restitution factors is very important. and it requires quite a bit of engineering experience and rock modeling experience to effectively come up with the right solution. You can see in the top right-hand corner that the blocks that are falling down that slope, once they're incident on the first bench, if you don't apply the right amount of scaling, or indeed the suitable coefficient of restitution in the first place, then the blocks can bounce off there like they're ping pong balls. And so you've got to adjust your scaling appropriately. So you can see on the bottom of that slope, applying the right factors gives you a much more realistic bouncing trajectory. And that comes with a bit of engineering experience, and where possible, if you've done some back analysis of the slope as well. Other things you need to put into your model are the friction angle of the material. When it starts to slide, does it actually slide or does it bounce? Other things you might have to look at is surface roughness, and this is something that you'll put into the older models. As I was saying previously, you didn't have that in your topography, quite a close handle on the slope geometry, and so you had to apply some of those assumed variations in asperity, height, and wavelength. So once you've got all of those parameters considered, you can then apply them in either a 2D application or a 3D analysis. So generally speaking, the engineer would go out to site to the area of interest where you might want to be controlling or pulling in your rock trap. Consider the condition of the face, the size of the blocks that are on the face and where they might come from, and whether it's any rock fall might be channeled into gullies which might dictate the direction in which it might move. So that was very much an engineering judgment on where the blocks might fall down the face. And I'll show you some videos later on which show that often the blocks don't just come straight down the face. If they happen to impact on a side of a debris pile or into a gully, they can be thrown off course quite dramatically. And that's why you might want to move from a 2D slope section line to a more comprehensive 3D analysis. So you apply to your slope effectively the coefficients of restitution. So you identify which areas are hard rock, for example, which are soft materials, which might be lying on your rock traps or on original ground, or you might have tipped some silt in behind a face to try and absorb the energy as well. Then you find where you want to apply your initiation points, and then let it roll down the slope. That's basically what you have to do. And then in a 3D analysis, this is an example that I'll show later on of the analysis that we did on down a slope in Scotland earlier this year, where the head wall of a rock buttress a few hundred meters up the slope failed and impacted on a dam on the bottom of the slope. But you do the same thing in the 3D analysis as you were doing in your 2D analysis, but apply the parameters in plan as opposed to a line in section. So you can see on this particular slope, any area which is original ground has on that the application of parameters which relate to more energy absorbent materials, because there's a thin layer of peat overlying the soils, generally speaking. In the areas of red, we've got fresh bedrock or clean bedrock, which has been exposed through washing down of debris material, and in purple, mixed debris materials, which are present because of the failure, and other screen and materials which are purely stacked blocks of clean rock as well. And we also apply, rather than just point seeders, area seeders from which perched rocks might come, but again in plan view as opposed to just points on the cross section. So I thought I would then just show you, rather than try and be any more analytical, just to show a few interesting cases that we've looked at over the years, both in the quarrying environment and some other more civil engineering type projects as well. So I'm going to start off with a site in Malaysia, Pahang Cement, which is up near the Thai border. And it's a Bardon Hill type environment. So that means it's got a it's one of these mountains that stands alone and sticks up out of the surrounding valley areas by several hundred meters. And you can see that we've got very steep sided slopes. And the quarry contractor is developing the site essentially by taking the top off an egg. It's working from the top downwards and reducing the floor level of the quarry. However, you can see at the far end on the northern side of this particular hillside, there's some slopes that have been left in place. And the reason for that is there's a lot of infrastructure just on the other side, which if blocks fall from that and the coal sheds and some of the processing areas at the bottom of the slope. Just for scale there, you can see some pretty precarious end tipping from the edge of that slope, with the guy reversing up to the edge without any particular edge protection and tipping materials directly over the face. And that slope there is about 300 meters high. So we've got quite a lot of rockfall incidents there, which we can do some back analysis on to try and derive some of the parameters. On the left-hand side, you can see, I'll show you a picture in a second, of the position of a cave, which just lies to the top of those elevated sections of the floor, which is lying directly above the coal reclaim shed. So here's a picture of the mountain from the bottom. You can see the coal reclaim shed at the bottom of the slope, and high up the face, the top of that crest we were looking at before is right at the top where the trees are, but in the face of the slope they've left below, you can see a large cave developed, and that cave is about 150 meters high, and that lies about 120 meters above the coal shed, and the coal shed only lies about 40 meters away from the toe of the slope. And below the cave there's a large ski ramp type feature, which if any material was to fall from the head wall or the crown of that cave, it would impact onto the slope at the bottom and then spill rather dramatically and fly out onto the slope below. So the client wanted to know what the likelihood would be of material falling from the top of the slope, because quite a lot of that cave area is overhanging and impacting on the shed at the bottom of the slope. Would he have to move the coal shed? Would he have to move his roadway between the toe of the slope and the coal shed as well? So this was an analysis that was done some time ago, and in doing it, so we used a lump rock, sort of lump mass analysis, so it didn't take into account any particular rock shape. But there's been quite a number of rockfall events, as I showed earlier on, from which we could back analyze the parameters to try and get a good handle on how the energy would be absorbed as it came down the slope, assuming the blocks didn't break apart and then impact onto the bottom. So if you've got rocks which have fallen down the slope and you can look at where they impacted at the floor, and higher up on the slope, you might be able to analyze where they come from and get some realistic parameters for inputting into your model. So what we were tasked with looking at is the overhead beam here. First of all, looking at small blocks, which were with the possibility of it coming away, and then also commenting on what would be the results of a large crown pillar failure if that whole section of the upper slope was to come away, and that was quite a few tens of thousands of tons of material. So just shown on there is quite a number of the critical 2D sections that we identified. That slope was, the geometry was defined using photogrammetry, both from the bottom and the side, and using some remote scanning survey equipment that I had available on site as well. So when you actually do the analyses, you see that blocks fall from the overhanging section incident onto the base of the ski ramp slope below. And the prediction was that there would be a number of blocks which would impact onto the top of the coal shed and across the access area along the toe of the slope. And that allowed us to define an area, a danger area from small failures. And you can see here where the actual line of the danger area was. We should be removing or relocating our entrance road from this area into the back area. And then following that, of course, there was a rockfall incident, and several small blocks came away from the crown pillar area and did bounce off the ski slope and impact onto the top of the shed. But the question remained, what would happen if the full crown beam was to fall from the top of that slope? And in such a circumstances, calculated it would be about 40 to 80,000 tons of material would be incident on the high slope of face. And what would be the result? I've got here a little video of a very similar situation in Malaysia. And we'll start off, hopefully it will work. You can see there's been a blast in the quarry, which is just behind the front of this slope, and there's some dust developing from the front edge, and then the whole slope starts to fall down. You can see that was quite a dramatic example of what would happen if a very large block of material fell from the slope. I'm talking about a few 100,000 tons of material there. But those massive falls give rise to large air blasts as well, and it's possible to throw large blocks of material for hundreds of meters out from the toe of the slope. So in that particular incident, I've just showed a position here, or a couple of slides of a 1-ton block, which was thrown 320 meters from the toe of the collapse. And in that site in Malaysia, where I was standing taking the photograph, I'll just go back a couple of slides. I was standing down here looking up that slope. You can see that if that whole face was to collapse, lots of that material would not only go over the top of the the coal shed, but would impact on the main railway line, which connects Malaysia to Thailand, and onto the 4-lane carriageway, which is immediately behind that as well. So the operators on that site have some careful excavation to do to avoid all of that material falling down the slope. So I just thought we'd look at the Bardon Hill quarry example. This is what some of my colleagues looked at earlier this year. You can see that it's quite a dramatic photograph showing the new Doppelmayr rope conveying system in place across the old Bardon quarry void. And the reason for that being there is that all the overburden from the new quarry will be tipped into the old quarry void. And the most efficient way of removing it is to take it via conveyor out of the old quarry and to the head of the corner here, where the conveyor will deposit material onto the rope conveyor, and that material will be then deposited into the bottom of the quarry. But with the rope conveyor, of course, you have a certain amount of bend in the whole structure to allow it to deposit materials at the bottom, and then as the bottom of the quarry fills up, then that is pulled up coincident with the rising level of the waste. But over up on the corner there, you can see where the initial pivot tower is. We needed to, or AI needed to cut a slot into the upper benches in order for the to accommodate the rope conveyor. And in cutting that slot, that would produce a lot of rockfall or potential rockfall, which could then fall over the face and then be incident on the main haul ramp, which is spiraling down the quarry. And the task there was to consider the size of an adequate rock trap, which would need to be designed in order to contain any of that rockfall, not only as it was being excavated, but also in the future to allow for access to the floor of the quarry, because you need to service your vehicles and bring fuel and all the rest of it down to the bottom. So here's the situation prior to any development in that area. The idea was to cut a rock slot down through the solid rock on the upper two benches. But budget and time constraints meant that the rock couldn't be raised to the crest and removed from the top. It was much more likely that rock material would have to be cast over the face in order for it to be mucked out and cleaned out at the bottom. So how to design a rock trap which would contain all of that material, avoid spillage onto the main haul road, because that takes time to mop up and clean up in order to then allow you to get down to the bottom of the slope and recommence work, especially during the formation of the slot. So we had a multi-belt situation here. You can see that on the left-hand side there's the slope was actually excavated using a Menzie muck walking excavator, one of these excavators on a sort of spider type carriage that allows it to go down some really steep slopes. And on the front of that, I had a pecker which was pecking out the ground, and also a bucket that allowed you eventually, once it had broken through, to cast material over the face. You can see that slope is got a number of benches, some of which are now filled with debris from casting material over the face. Just looking from the top down, you can see the situation. We've got the rock slot beginning to be formed in this area, material which is fallen over the face as that rock slot has been developed, and the construction at this point of the designed rock trap at the bottom of the face. And you'll note that this happens to be in the corner of the quarry, so you've got a bit of a slot down which it goes, but being in the corner, you've got some curvature to the lower benches, which means that you can't just do straight line sectional analyses, because ultimately once those benches start to fill up debris and material starts to slide off, not directly down the face, but laterally it might then go off in an unexpected angle, and so 3D analysis later on would be appropriate as well. So this shows an example of the initial 2D analysis that we undertook in order to size the rock trap at the bottom of the slope to contain material, leave the sufficient room to allow the road to remain open with a minimal amount of spillage over the top that needed to be cleaned up in order to allow access down into the bottom. And you can see there are some trajectories there that show that there are particular rockfall trajectories which will overtop not or miss out a couple of benches, and so the rock trap needed to be sufficiently far away and high enough to try and catch those. And the analysis shows here some of the initial benches being filled up with debris from the upper slope, and in those cases you can see that you need to have quite a high 4-meter plus rock trap in order to contain any of that or most of that debris that's coming off the face. Not only that, we found that in order to maintain the access road, you would have to have quite a steep inner face of your rock trap, and to get the height, you want to have that as the footprint as narrow as possible. Sorry, in order to maintain the road width, you need to maintain the reduce the rock trap width to as narrow as possible, which meant the ultimate design was a combination of gabion baskets and materials placed on top, which would be energy absorbent as well. And the solution was this system of HESCO gabion baskets, which are concertinaed gabion baskets, which are filled or are geotextile lined and can be rapidly pulled out in the matter of minutes over 50 or 100 meters, and then backfilled with dust materials, and then you can heap your other rock trap forming materials on top of that as well. So the whole slope can be formed, or trap can be formed fairly rapidly and flexibly in a couple of, within a day for a 50 or 60 meter section. So you can see that the initial design had a steep inner slope and a section which of the upper slope, which allowed for incident to try and contain the blocks which might overtop numerous benches or the intermediate benches. So I've already said this, the ultimate design was to install a 4-meter rock trap, the lower section of which, or the inside section of which, was formed by these 2-meter high HESCO geotextile lined gabion baskets with fines placed above it to give us the ultimate 4-meter high rock trap, and that reduced the overall footprint of the bund. You can see it being formed here, just going around the corner there, quite an open, clean slope there at the moment. Sorry, a closed trap ready for containing any materials which were going to be cast over the face as the rock slot broke through from the as the Menzies muck was excavating into the slot. Most of the materials initially went to the side, but as we broke through, we needed to be able to contain as much as possible the rock materials coming over the face. So I've just got a couple of videos now, hopefully, which will work to show you how rock actually fall from the face. You'll probably see that actually rather than blocks bouncing a long way out from the bottom, from the face itself, as is normally as you often get in unregulated rockfall analyses that have got any scaling on them, that the materials actually when they fall down the face closely, or don't bounce very high off the face, they either slide or they bounce only a couple of meters out from the face. So let's have a look at a couple of examples of blocks falling down the face. The road is closed off at this point to prevent any material coming down. You can see an equidistant block, or equi-shaped block, overtopping the bottom benches and impacting into the bottom, and rolling up onto the top of the rock trap, but then ultimately falling back into it. It's normally the material is just falling down or sliding initially, and then some materials roll, and again it'll bounce off your ski ledge and overtop a couple of of ledges, impacting on the lower debris pile, sometimes breaking apart, but sometimes maintaining its integrity. The next video shows another section of material. I think this one shows a block impacting on a block perched on the slope there. As you can see, that's just causes incidental rockfall. Another example here, where materials are coming off from the side, and this, rather than falling down the original slot, comes down a gully to the left-hand side, away from the predicted initial areas. If you were just doing a 2D analysis, that's why you want to look at a 3D analysis, because materials come away from the side. And we can have a look at an example from the drone itself. And you see this block rolling end here. Doesn't go anywhere near the original line of down which it comes. It's controlled by a gully to the left-hand side on the picture, and rolled end on end down the side of a rock pile, and then incident into the rock trap at the bottom of the slope. And you can see what's happening. Most of the material is being held within the rock trap. There's some debris which has gone over the front, and which has been scraped back and pushed to the corner. But essentially, all the material is then falling into the rock trap. Any material, of course, the road was closed when all of that material was being cast over the face. Just go back to the presentation, hopefully. We can see some of the 3D rockfall analyses which were undertaken, and of course that showed that quite a lot of the material falling from the face would incident on beyond the rock trap once it was filled with debris, and onto the road itself. Incidentally, you can see to the left-hand side here, very similar to the last video that I showed, that one of the blocks that has come off and is modeled here goes off down the side of the debris pile, and then bounces away from the initial line of which you would assume would be your most critical line, and has a different rock path to the bottom. So there's a need evidently here for 3D rockfall analyses, because that then accommodates changes in topography outside your initial rockfall line. So once we'd finished all of the breakthrough from the slot, I think the bottom of the all of this material in the rock behind the rock trap was dug out and cleaned out, and then we resurveyed that slot area, so we got a good understanding of the geometries of the debris piles which have been forming on each of the benches. So we could then rerun the analyses and adjust the rockfall protection at the bottom, and you can see that of the 840 blocks we modeled, only about 1.5% of blocks actually overtop that the current design, and of those, the majority of those were hitting a feature right at the bottom on the right hand side here, which is a low shelf, which we then subsequently covered with energy absorbent materials to try and prevent that going over the top. And 1 year on from the installation of the rock trap, there's been no rockfalls which have gone beyond it. So I'm just going to move on to this I think we've got time. This rockfall analysis that we did at Loch Cuyock up in northern Scotland. This is really quite an interesting project because of the size of it. The failure initially occurred in 2018, and materials from a head wall rock slope right at the top of the valley, some 370 meters above the road level, failed. And all of that material, which was the best part of 3,000 meters cubed of material, flowed very rapidly down the slope, controlled in the most part by the gullies that were present on the pre-failure ground surface, down the slope, and impacted onto the road at the bottom of the slope and into the spillway, but fortunately not onto the dam at the bottom of that slope, but also impacted onto a 132 kilovolt electricity pylon electric line, which was the main electric line to the Isle of Skye. So they needed to repair that in fairly short order. And to repair that quickly and get the power back on, the electricity board installed a series of temporary pylons across the bottom of the slope. Yes, the original failure, this is a shot right at the top, showed a section of about 50 meters length and the order of 3,000 cubic meters of material having fallen from the slope, a mass toppling and planar failure, which acted more as a debris slide than it was individual rockfall. So last year, or later this, I went out there last year to have a look at it, and I went back up this year again to have a look at the condition of the upper slope, because the temporary wooden pylon sets were going to be removed, the electricity board having installed some large mega pylons which span the entire rockfall risk area. But they're still going to have people working in and around the areas of the temporary pylons when they decommission them. So going up to the top of the head wall, you can see that when we did the inspection, quite a lot of potential for further slope failures, which would give rise to individual rockfall events. In the 3 years since the failure, quite a lot of water has flowed down the slope and cleaned out the gullies and cleaned off the debris from the bedrock, which would strip clean during the initial failure. And it's quite a steep slope, and there is a potential for rockfall to reach the bottom of the slope. So quite a number of areas where rockfall could initiate from, both from the virgin upper slope and from other piles of rock debris, which, if incident from higher up, might result in further unraveling down the slope. So the thing to do was to map the general area, determine, first of all, what an accurate topography was derived using UAV survey, and then map the area to look at the areas where different materials might be present on the slope. So the red areas are clean bedrock, the purple area, mixed debris from the previous failure. And also we identified areas where you might have release of blocks from failure from undermining, from stream flow, from already piled up materials, or from the head wall itself at the top of the slope that might give primary rockfall incidents. You can see at the bottom of the plan the position of the 3 sets of temporary pylons, and the electricity board wanted to know what the wanted a quantitative assessment of what the likelihood, what the risk would be to anybody working in and around those areas. And in order to assess that, we constructed buffer zones around the pylons, which were 10-meter standoff and a 30-meter standoff. So once you've defined your rockfall areas and the material characteristics, and of course we had some information from the back analysis of the previous failure, we were able to then do some rockfall analyses to see where the materials might flow. And of course, you need to have in this situation a 3D assessment, because the geometry is very much governed by the presence of all the gullies at the bottom of the slope. So we did a number of these analyses to see where the rockfall might develop. And once you put them all together, then you can use some GIS type software to look at the number of incidents within the danger zones or buffer zones in and around the temporary pylons, like we did here. And you can see pretty much there are incidents into all of those areas, controlled largely by the positions of the pre-existing gullies. But then you need to consider the number of blocks that might actually go into that area. And what we found is the 2 westernmost areas were going to be pretty much protected from by the position of the gullies, but the right-hand one, or the most eastern one on this one, which was QB 280, did have quite a number of incidents, or an appreciable risk that it might enter within 30 meters of it, outside of a gully area, incidentally. And there was a pretty low risk that it would enter within 10 meters, that area. So as long as you could construct an access to get you into there, which wasn't going to be impacted upon by those rockfall events, then it would be safe for them to do so. And so back in September, they went into that area and cleaned out those temporary pylons. So very quickly, just at the end here, we've got another rockfall assessment in an area and a quarry where there was a access road into the sump area above a high wall, which was beginning to deteriorate, and the client wanted to know the geometry of the rock trap, which would be required in order to deflect the majority of that rock, or contain and deflect the majority of rockfall onto the road at the bottom. So you do an analysis which shows what the current risk might be, and very much the same as the Loch Quinnock example. And then an example here, once you've installed your rock trap to the correct geometries, you can reduce the risk of anything overtopping it to an acceptable level. So hopefully there were a couple of examples of how you might want to use 2D and 3D analyses when you're moving away from the generic rockfall type design. And I just thought I'd end up by showing those, particularly for North Wales, that there's nothing new under the sun. The multi-million-pound Doppelmayr rope conveyor slot that was cut last year for the works up at Bardon Hill. They did the same thing on a site to form a rope cutting for a slate quarry in the 1900s. So that's a picture that I took when doing assessment earlier this year. So thank you very much for your attention. I hope I didn't ramble too much.
Thank you, David. That was very informative, very interesting. And thank you very well. Does anybody have any questions to put to David? Well, don't let him get away with it.
I must have explained it very clearly.
Yeah. There's nothing come through on chat, I don't think.
Oh, great.
Well, must have explained everything very well, David.
Oh, yes, hopefully.
Yeah, that was
Great.
brilliant.
Well, I was hoping it wouldn't be too dry, and there were some interesting examples, which are a mixture of individual face failure, slope assessment, multi-bench rockfall assessments, and a whole slope, side of a mountain type assessments that you might consider, different 2D and 3D rockfall analyses, and also consider the evolution of that over the years as well.
Yeah, that's brilliant. One thing that stood out for me was that machine driver and that spider.
Oh, yes.
Nerves of steel.
You just have nerves of steel, but I'm very, very competent and quite used to that sort of situation. I think that type of machine adopted for use in the Alps on extremely steep slopes.
I have seen it somewhere else before, so in pictures, and I thought, then no, that would not do for me.
Yeah. Great.
I think we had a question come through.
There's something in the chat. Basically, any damage to the Gabion wall when the Bardon Hill rock trap was cleaned out?
To be honest, I can't tell you, because it wasn't the project. That's the one project I didn't look after, so I can't. I'm sorry, I can't tell you, but I might be able to follow that up. But again, as I say, they're quite rapidly placed, so any sections that you need to repair, you could dig that out, snip out the bit you need to move, and pull in a new gabion within half an hour. If you've got, it's really quite a rapid situation, flexible solution.
That's good. I don't know if there's any more questions coming through. You've given it quite easy at the end, David.
Great.
Oh, that's great stuff. Well, thank you once again, David, for giving up your time. Much appreciated.
You're very welcome.